Thank you. Thank you, Katya. Thank you for the invitation. And I'm grateful to the organizer for the opportunity to speak at the seminar. And this talk, as I said in the abstract, is based on joint work with Gunther Ullman and Iran Wang. So this was during the time we were at MSRI, Gunther and I. So we're going to talk about scattering for semilinear wave equation. So in general, as as in the linear case, of course, solutions exist globally, but of course, in the nonlinear case, you have to, if you want to study scattering, you have to study the existence of global solutions, at least for small data, and then once you do that, you want to know if this is asymptotically complete. So in other words, you want to know if as time goes to plus or minus infinity, the solutions behave like solutions of a corresponding linear equation. So, but of course, this is a difficult problem in itself. It's not always the case that solutions exist globally, and even if they do, it's very hard to, also you have to prove the asymptotically complete. So this is a difficult problem, even the direct scattering. So but of course, you'd like to ask, if you have a scattering, a well-defined scattering operator, you like to ask the inverse scattering problem. So given a nonlinear wave equation, for which there is a well-defined scattering operator, even if only for small data, you like to ask the question about, what can you say about the equation from its scattering operator? So of course, a more modest question is the problem of determining a nonlinear potential. So, and this is the case I'm going to talk about. But even in that case, we would like to consider the case of a semilinear wave equation of this form. So you have the wave equation, you have a potential H, depends on U only, and n times U. Even this case that, is a very particular case, but the problem is that if you allow this potential to depend on time and X, then you have a series of counterexamples that there's no scattering or something. So we will restrict ourselves to this case where the potential depends only on U. And then so there's a long history of work on this problem of determining for what class of potentials the scattering is well defined. And as far as I know, this goes back to the work of Strauss, 1968. Maybe before that, I don't know. So this is the reference I have. I'm not really a specialist in this nonlinear wave equation, anything. But so the important case of H of U equals plus or minus that, even so now you take the absolute value, and this you take for complex solutions. This case has been intensely studied. So the equation with the plus sign, so this means this potential here is positive, is called defocusing, because it has a positive conserved energy, nonlinear energy. And the ones with a minus are called focusing, because the energy is not, the conserved energy is not positive. And this is focusing case is much more complicated, and I'll not talk very much about that. But I'll not discuss this question either. I'm just going to restrict myself to one particular case. So the particular case we study is this case, where you have this wave equation, and this function f of u behaves like u to the fifth. So, like I said before, this term f of u is equal to, maybe you can, f of u is minus u to the fifth, is of course is very different because what I said, the energy, the positive energy, the conserved energy is not positive. So this power 5 is called critical because this scaling leaves the equation and the conserved energy invariant. So in this case, so it's a case where this sign is positive and it behaves like that. So of course, it's interesting to know that nonlinearity is in higher space dimensions, but I will not say anything about that. I'm just going to stick myself to this case. And then, but now the precise conditions of this function, f of u, and we call this condition CF, this conditions on f. So to be able to define this scattering operator, we shall assume that f satisfies the following hypothesis. It's an even, it's like this, f is of this form, where h is an even function, so that means f is odd, and h behaves like this, that the u times the derivative of u of f behaves like f at infinity and at 0, and this integral, which is the corresponding the integral of f. So for example, in the case u to the fifth, this g of u will be u to the 6 over 6. So you want this to be a convex function. And also the derivatives of f are bounded by this. Oops, sorry. Oops. What did I do? My mouse here is sort of very sensitive. Forgive me. I want to make it bigger. Yes. I somehow. Is it okay like this? Or okay, sorry.
It's great.
Okay, so now it's the opposite. Okay, is it okay this way? Anyway, so now under these assumptions of on the function f, so there's the work of Chata and Struve in 93 and 94. So this question about the scattering and the global existence was settled in the 90s, and then by these people, Chata and Struve. There's the Bowery and Chata in 1998, Bowery and Gerard in 1999. He examined the well posing of the Cauchy problem for these spaces. And there's also the work of Grylakis. Grylakis proved the global existence of smooth solutions, and that was preceded by the work of Struve also for the radial case. But here I want interested in this spaces here. So this is the standard energy, finite energy space. But now you have the you have this additional LP-LQ space, which is Strickard norms. So your solution in this that this sort of standard energy, and then you have this Strickard norm that you have supposed. And you have the same version of the local space. And then the original work is for this function, but if you go look at the proofs, you can see that they work for function that satisfies the condition CF I mentioned above. And this was Patrick Gerard alludes to this in his 1996 paper. So, and then Chata and Struve, complemented by Bowery and Gerard, they prove that under these conditions, for any initial data, now is you know, there's no, this, it can be very large. The energy norm can be anything, but you have a unique solution, U, in this space, satisfying the semilinear wave equation. And then, but this was Chatain's proved this existence in this space, local. And then Baury and Gerard showed that in fact such solutions are global in this norm. So these are known as Chatain's true solutions of the semilinear wave equation. There's still a problem here, you know, in this case where you don't have this Strickard norm. So it's not, you know, the existence uniqueness for solutions that are not in this class. As far as I know, it's still an open problem. For example, if there are solutions that are not, have finite energy but are not in this L5, there's work about uniqueness by Planchon and some others I forget right now about uniqueness of that. And then in the radial case, there is no distinction between these two cases, these two things. And this is the work of Genib, Soff, and Velo in 1992. So in the case where you have the solution is the initial data is radial, then if it's the data is finite energy, then it is automatically here in this Strickard space. So the asymptotic completeness of the Chatain's two solutions was established by Baury and Gerard. They showed that if this function obeys the conditions I mentioned above, and then you have finite energy Cauchy data, and if U is a solution corresponding, if the corresponding Chatain's two solution of the semilinear equation, then you have a pair of you know, phi 0 plus or minus, psi 0 plus or minus, of finite energy, such that if this V plus or minus a solution of the Cauchy problem for the linear equation, right, then the energy norm of the difference of the solution of the Chatain's true solution of the semilinear equation and the solution of the linear wave equation, the energy norm goes to 0, it goes plus, and then it goes the same thing for the minus, it goes to 0 here. So this is and then they of course they define this wave operators, omega plus or minus, which is sends the initial data of the corresponding linear equation to the initial data. Okay. Thank you. Sorry about that. So this is so these are isometries, and this is the limit as usual. Of course, this is non-trivial because you know this is a nonlinear group. Right? So so the key to this is that this energy. So if you take the nonlinearity, you integrate that. So for example, in the case of u to the 5, this will be u to the 6. If you take the integral of u to the 6, and then you integrate in x, and then you let the limit go to p goes to infinity, this goes to 0. So this means that the nonlinear energy part, the nonlinear part of the energy goes to 0. So that's why this is an isometry. And so, and then you define the molar semilinear scattering, was defined in this form. Of course, as standard, you have omega minus inverse composed with this one. And then, so the theorem joint work with Gunther Ullmann and Yiran Wang, says that if you have two FJs U, which are of the form described above, satisfying those conditions, then we have to make this assumption here, and I'll explain later why. You have to make an assumption about the set of zeros of the fourth derivative. And then you say that the set of points where the fourth derivative is equal to 0, you assume they are countable. I mean, I suppose this can be relaxed a little bit, but the proof we have right now, it cannot be relaxed too much. For example, you cannot replace this with measure 0 or even content 0. And then, so now if you take the two Müller scattering operators, if the scattering operators are equal, then the functions are equal for U. And then, so the previous results, known to me at least, are for real analytic nonlinearities. And this is listed in alphabetical order, but I think in chronological order, the first result I'm aware of is this paper by Moravec and Strauss, 1973. And this is for the Klein-Gordon equation, where they prove that the scattering operator determines that actually what they really prove is that it determines a coupling constant. So they just have a constant times the potential. I don't remember exactly what the nonlinearity is. If it's U to the fifth, maybe it's U to the cube. I don't remember exactly what but anyway, so this is the first result I'm aware of. And this was extended by Bachelot also, but for the Klein-Gordon equation, again, for the real analytic nonlinearity. And there's this paper of Ricardo Wede, also for Klein-Gordon. But this is pretty similar to this result of Bachelot, except that he adds a linear potential to the so it's not just the wave equation, but it's a wave equation plus a potential, and then plus a nonlinear term, which is real analytic. And then this paper of Gallagher and Remy Carl and Isabel Gallagher, this is the one that has the most influence on what we did. So they studied, they're not concerned with Neve's problem. This is really an sort of a corollary of the theorem. But they are really interested in the analyticity of the scattering operator. But they do, well, the main point in those papers is that if the function f is real analytic, then the molar scattering operator is real analytic in the sense that if you have W0 and W1 in this space, the finite energy, and epsilon is small enough, and m is the molar scattering operator, then you have that m of W0 plus epsilon W has an expansion like this, and the series converges strongly. And from this coefficient, one can determine the Taylor series of f at U at the point at 0. So this, of course, this is quite hard to prove because it involves global estimates. And then in most papers I mentioned above, they linearize about 0, so the W0 is just 0. But Carl and Gallagher show this is true for any W0. And they do this for several equations, include the wave, the Klein-Gordon, I'm sorry, I misspelled Klein-Gordon, and Hartree. And then, but they only do this for U to the 5. It's a polynomial, the nonlinearity. But it extends if the function is real analytic. Of course, you have to assume the equation has uniqueness, and the solution exists, so you can talk about scattering. Anyway, so So our plan is to prove an analog of this expansion here, but to find an order only if F is not real analytic. And then the second part is that we use the methods of Kurilev, Lasses, and Ullmann, and Lasses, Ullmann, and Wang. And then, so the idea is to use singularities of some of these terms in the expansion to obtain information about F. However, you see, the Moleck operator is not quite suitable for this, at least not to me, that it's not for tracking propagation of singularities. So you like to rephrase, instead of using the Moleck operator, you want to use Freelander radiation fields. So in the case of the linear equation, so let's recall the definition of the Freelander radiation fields for the linear equation. So, in the linear equation, you have dt squared minus Laplacian of v equals to a forcing term. So v of 0 is phi, and dt of v0 is psi. This suppose that is a infinity compact support. So you define the forward and backward radiation field are defined to be this limit. This is R. Is the limit of you do this risk. So this is should be the opposite. I'm sorry. This R plus should be minus here. So the backward, because as R goes to infinity. No, this is correct. Yes, so this is correct. Sorry, this is correct. So this is a S plus R, and this is the other one, is S minus R. When R goes to infinity, it goes to plus infinity. When R goes to minus infinity, it goes to minus infinity. So this is the forward and the backward. R, of course, here is the polar distance, and theta is this. Okay, so now, let me explain why this is, the radiation fields are it's very good to study propagation of singularities. So if you think about the variables, S, R, and omega, S, of course, is T minus R. So you take the time and you shift by this. So this, of course, is the light cone, right? T equals R and T equals minus R. So you're looking at the limits of how the solution behaves along this light cone as R goes to plus infinity. And if then you conjugate the operator this way, of course, this power here is because I'm talking about dimension 3. In general, I think this is n minus 1 over 2. So your operator reduces to this. And then if you compactify a x to be R minus 1, then this operator becomes, this has this form here. This, of course, is a natural extension to a neighborhood of x equals 0. So now if you look at the Hamilton vector field of this operator, and I call the principal symbol rho, this principal symbol of this operator P, is this 2 mu psi. Mu is the dual to S, psi is the dual to X. And then you have, of course, I should, I really should have a minus here, but this is okay, sorry. This is minus the symbol of this operator. And then you have age, which is the principal symbol of the Laplacian on the sphere. This is more general, of course. This discussion here holds for, for this class of manifolds that Melrose introduced, this asymptotically Euclidean manifold. So now if you compute the Hamilton vector field, you see that this is what you get. The key thing now is the following, is that on the characteristic variety of box, and away from the 0 section, you have tau squared is not 0. So tau, but tau is equal to mu. So we conclude that near x equals 0, when we go back here to the form of the operator, so this mu here is not 0. So when x is 0, this is 0, of course. So this means that this is transversal to x equals 0. So this Hamilton vector field is transversal to x equals 0. So for example, so if you have a Lagrangian submanifold, is containing rho equals 0 rho, is sort of unusual. is the symbol of the operator. So it's a characteristic Lagrangian containing in rho equals 0. And then this vector field is tangent to to lambda. Then, because the lambda is, the vector field is transversal to x equals 0, then this lambda extends across x equals 0 as a C-infinity Lagrangian. And there's a union of integral curves of this that start on lambda for x bigger than 0. And so, in particular, you see the restriction of the Lagrangian. If you have a Lagrangian distribution with respect to this manifold, lambda tilde, the restriction to x equals 0 makes sense because the Lagrangian extends here. So if you have u, to be as a Lagrangian distribution with respect to this manifold, and so if phi parameterizes lambda tilde in the sense that, as usual, the dictator phi equals to this. And then when you set x equals 0, this phi of 0 s omega theta parameterizes lambda infinity, and u restrict to this is given by this oscillatory integral. And so that you can compute, if you know this symbol, you can compute the symbol of the restriction, and that's what it is. Since the dimension drops by 1, the order of the Lagrangian distribution goes up by 1/4 according to definition of Hermander's definition of the order of the Lagrangian distribution. But the important thing that we use is that if the Lagrangian distribution is elliptic, so is its restriction to 0, to x equals 0. So if you go back to the radiation field, right? So if you have a Lagrangian distribution, if you go back to the definition of the radiation field here, which we had before, so this limit, if you think about this is, so when r goes to infinity, this corresponds to the restriction at x equals 0, right? So you take r to be 1/x, and then you're taking this and you restrict this to r equals 0. So if this is a Lagrangian distribution, which is a characteristic Lagrangian, then the radiation field is you restrict this to infinity as well. If you know the symbol of this thing, you know the symbol of the restriction to x equals 0. Now, this is, of course, roughly speaking, but that's the point of using the radiation field. So if you know this, if you know the B is a Lagrangian distribution, then you know that the radiation field will also be a Lagrangian distribution. And so, okay, so now you can also define the Freelander radiation field for the semilinear wave equation. And this is going to work with Dean Baskin from 2015. So we show that if you do this for the nonlinear wave equation that we're talking about, right? This here our function satisfy CF, the conditions on that function. And so we show that you have the initial data, and then this is the Chatas-Stroop solution, then this limit exists, and then in this energy space. So this had been, established, proved by Grilakis when you had, so you see this limit exists. So Grilakis proved this for functions that this statement for, I thought I said it here. This was shown by Grilakis in for initial data, which are smooth and compactly supported. So he proved that. We just extended his result for a function that are finite energy, and then but now these operators are isometries, but with this energy norm. Again, I mean, the point here is, as in the case of asymptotic completeness of Bauri and Gerard, that the key thing is that the integral, this term here goes to 0. So this is again it relies on this. I mean, there's this essentially is in the paper of Bauri and Gerard. We just rephrased this in terms of the Freelander radiation field. Of course, now we can define a Freelander semilinear scattering operator in this form using the radiation field. And then we show that you can get one operator from the other by conjugating with the linear radiation field. So if you have the molar operator, you conjugate on one hand by this operator, and this is the radiation field correspond to, here's the initial data, the forcing term is 0. So if you know one operator, you know the other. So, and this is the second version of the theorem, of course, which is the same as before, except that now it's phrased in terms of the Freelander radiation, in the Freelander scattering operator. So if you have, if the function satisfies the properties we mentioned above, and the two Freelander scattering operators are equal, then F1 is equal to F2 for all U in R. And now, so here's, so let's go back to this linearization. This is the analog of the result of Carlin and Gallagher. So it says that suppose that F obeys the conditions of the CF above, and Yj are functions in L2, not Yj, I'm sorry, epsilon j are functions in L2, and epsilon j, now you see here that the spirit of Kurilev, Lasses, and Ullmann here, that now we take, instead of one epsilon, we take several of them. And then you have j equal 1, 2, 3, and 4. And this is epsilon that is small enough. And A is the Freelander scattering operator. So you take A applied to epsilon 0 plus the sum. So then you have epsilon j, then you have this plus this expansion. Except that now the expansion goes only up to 4. And then we prove that this is equal to this, and the remainder is of the order 5. This is a bit of work because, this is, of course, global estimates, and we have to, use a lot of Strickland estimates and so on. But in essence, this is a la Carl and Gallagher. So there's a big influence of the work here. So now how we pick, now we have to pick those things. Remember, so this was part of the plan. The plan was to use this formula and then use the propagation of singularities. So of course we have to choose those things carefully. So of course the background solution, we pick initial data, which is, no, I shouldn't say initial data, I should say data at infinity. This background is epsilon 0, we pick it to be radial, and then of course, we are an advantage here because we just want to determine a function of one variable, which is but then but we also impose this condition. I'll explain to you in a second why has to be the case. So epsilon 0 is the derivative, of course, because of this, is the derivative of a function which is infinitely compactly supported. But this set is good enough because it's dense on L2 of R. So the background solution, so now you give this data here at infinity. So the background solution satisfies this equation. A box of U0 is equal to this. And I'm denoting this N minus to be the backward radiation field. So for the lack of a better notation, this is like, I'm saying that the limit of this as R goes to infinity as before, right? Of that expression is given by this. And this, of course, so if you prescribe this at infinity, then this is this. And now you see, so this is shows to be radial and smooth, and the Châtard-Stouff solution corresponding to this is unique, is also the unique one with finite energy, because you could think there's something, strange, sneaking in some other solution, but in this case, there's no distinction between them. And now so we need, this is a lot like a flavor of the boundary control method in some sense. So, we need the following support and regularity theorem for semilinear radiation field. So this goes back to the work with Dean Baskin. So we have the control and regularity for nonlinear equation. So if you take this special data, which is an L2 function, and suppose it's compactly supported and satisfy, I'm sorry, this is not G, and this should be epsilon 0 here. So satisfy this integral equals 0. So let U0 denote the corresponding solution of the nonlinear equation. So this equation I just wrote above. So now if you take the initial data corresponding to this solution, then these are compactly supported and radial. Moreover, if this function is infinity, is C is 0 infinity, so are the initial data. This may look strange because you think about the radiation field, right? You remember the radon transform. Well, the radon transform here, is very special because this is radial. So of course you know that there's no the radon transform for a general function. This is not the case because you have the radiation, you have the radon transform, can be compactly supported, but the function cannot be, or may not be. But in this kind of radial function, this is the case. And you see that if this, so the spirit is the following, that, if this function is compactly supported, right, it's written like, sort of a, the derivative of the radon transform, roughly of one of this data psi, and the second derivative of the radon transform, this data. So one is odd and the other one is, the other is even. So it means that if this function is compact supported, then the radon transform of the derivative of the radon transform, this one is the derivative of radon transform, the other one is 2. And the second derivative, sorry, the second derivative of one, the first derivative of the other. And then this is the reason why this works. Of course, there's no chance of this being true if the data is not radial, of course, because it's not even true for linear equation. So now you have to pick the other ones. This one, of course, are not smooth because we want to track their singularity. So in general, you work with plane waves because when you're looking, but here it's not plane waves are not very good because, you know, the radiation field of plane waves is sort of a strange object. But we work with spherical waves instead of that. So these waves, you start a spherical wave at infinity, and then they collapse to a point. Of course, the cone, right? So you start with something at infinity, it collapses to a point, and then it expands again, and Friedlander called these hourglass waves. So you pick now you have to, you know, pick this at infinity. So these are your y epsilon j's. These are given by this formula, and you know, of course, I'm going sort of backwards. This, of course, is the radiation field of such an element. So this is a spherical wave, right? T minus Sj. So Sj is fixed. Is some you choose. T is, of course, time, and this Zj is also a point in Rn, in R3. You know? So Sj is in T, is in R, Zj is in R3. So you have, this is like the vertex of the cone. And so you take this, right? And then if you compute the radiation field of this element, that's exactly what you get. So this is the radiation field of this. And then you can see, I mean, it's not very hard to do this. It's just that you look at the asymptotics of these expressions. So you see that the limit of this function here is exactly this thing. So you take these waves in the, you know, the radiation field at infinity. Now you go back to your linearization, right? So you do this. You write U as U0, which is the background solution, plus this. And you know, it satisfies this. So now you write something like that, right? And now you do your Taylor's expansion, but only to order 4, and then you get this error here, which is of this form. And now you write, if you write Y is this way, so, and then you write epsilon is this vector, epsilon is this. So now you want U to be U0 plus this thing, where this is of this form. You substitute this in here, and then you know, you track out, you know, you match powers of epsilon of order 4, and then obtain global bounds for the remainder. So again, this is a lot of Strickland estimates and things like that. And then, so you get the following. So the terms of order 1 are defined this way. Yeah, so you get it's a linear equation. This is the potential, right, which comes from the derivative of this guy. So, you know, this potential, if you think about this, is a strange potential because, you know, it's contained in a cone. I mean, it's supported in a cone, right? Because U0, remember, has compactly supported initial data. This potential behaves like that. And then, you know, if you go back to the work of Greylakis, he gives you the rate of decay of U0, basically decays like order 5. I'm sorry, order 1. So the potential is the derivative. So it's like a decay of order 4 and supported in a cone. So this is not a very friendly potential. You know, it's not your standard sort of a compactly supported potential. So. But anyway, so but then we prove that, you know, given U0 is in this thing, right? Remember, this is in the space, the Chattaz-2 space. You know, of course, it's a linear equation now. You do this. So it's important to realize also that, you know, you're not really tracking singularities of the solution itself. We're tracking singularities of these terms, which is you're filtering these powers of epsilon. So now you go, this theta alpha is, of course, is the forward radiation field of this alpha here. Okay, so now, of course, you do second order. And then the second order is like this. So now you have the same linear term, and you have these products now of a previous term, right? So these equations are linear. So now you have this U0 and W beta 1, beta 2, other ones obtained before. And now you can, so the point now is that the second term, you're still taking products. You see, the point now is that you take products of conormal distribution here. So the W beta 1 and beta 2 are conormal distributions. So of course you do, so you take products of them, right? So this of course these cones, you know, these upsilon j's, you choose them so that they, you know, they intersect transversely, of course. So these products do not produce anything new, but now comes the third part. So the third part, so the third part is again the linear part, and then this term here, which comes from previous interactions. So now, as I said, so these terms are the ones can come from this double interaction times the one that comes from one just no interaction, right? And these are the one that, you know, is the one that have products of three of them. So now we rely on the work of Lassa's woman and Wang, said that the top singularity of the term W111 comes from this guy here, okay? So now you go there, and then you say these waves are elliptic conormal distributions. They're the ones with gamma 1, so this one's here, elliptical normal distribution with respect to the cones, and these cones intersect at a codimension 1 submanifold gamma. So you have products of this thing. Right? So this will have a singularity on this submanifold here, gamma. And now, according to the work of Melrose and Ullmann, so about, you know, a paired Lagrangian distribution. So you have a singularity will emanate from this, and this will be a Lagrangian distribution associated with Lagrangian submanifold determined by the union of the null bicharacteristic emanating from this set. But one can compute this principal symbol. But now you go back and you see that now you look at this, what happened to the Freelander radiation field. Right? So this determines this F cubed. So now you see you determine this nonlinearity, the derivative of this for every t and x in gamma. So if you vary the points Sj and Zj, you show that this determines this thing for every, you know, this gamma, of course, will sweep all R4. You prove that this is true. And now you repeat the same procedure instead of 3 waves now with 4 waves. And now with 4 waves, you show that you determine the 4th derivative. So you have the 3rd derivative and the 4th derivative. And here's what I would say the crux of the proof is this. So if you take your FJs to satisfy the hypothesis of the you know, about the function f, then given y0, upsilon 0, independent of w, so this is radial, with this property that it integrates to 0, and then you have initial data, which are infinity, such that the radiation field of this is upsilon 0. And then you take the solution uj corresponding to this. So this is what I call the background solution, okay, corresponding to this upsilon 0. Okay, so of course you have the same upsilon 0 for both. And then, so now that AJ denote this, the Freelander scattering operator associated with this. So if A1 is equal to A2, then the 3rd and 4th derivative satisfy this. Okay, so now you want to use this to show that F1 is equal to F2. And this, of course, well, once you prove this result, in particular for t equals 0, you have this, right? So by differentiating the first equation, you differentiate this equation in respect to s. I'm sorry, respect to, would be s here. Then we obtain that f4 times this of the first function is equal to the f4 of that function. And so as long as you can guarantee that this guy, remember those are equal, right? So this fellow, you can cancel them provided they are not 0. So a psi1 prime is equal to psi2 prime away from these things. So for example, so this is where, now you need this assumption on the zeros of the first derivative. So if these guys are, these guys are countable, and then you can show that these functions are equal to each other outside this set. But of course, then it's not very difficult. It boils down to this. If you take the difference of the two functions is equal to Cj on this union of these intervals outside of the set of zeros, it boils down to showing that you have this thing that is a significant function with a countable range, which of course implies that it's a constant. So this means that phi1 is equal to phi2. But of course, remember that you see, this was again this set of y0 here, chosen this is density null 2. So of course you can produce any phi, by density argument, you can prove, this data, anything you want. So this means that this implies that F1 is equal to F2. And that's all I had to say. Thank you very much for your attention.
Thank you very much, Antonio, for the very interesting talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Are there any questions or comments, please?
Okay. This is Rakesh from the University of Delaware. I had some questions. Again, so these are, sorry, okay. So I didn't fully understand everything you said, but does your nonlinear equation have a solution corresponding to initial data coming from incoming spherical waves?
Say it again, I'm sorry. Yeah.
So there are solutions to your nonlinear equation corresponding to initial data with, say, incoming spherical waves, say, for the u to the power 5 problem. So I didn't fully understand this part. Am I correct?
No, it does. I mean, as long as it's, yeah, I mean, you see, they are, it's not a delta function. It's like, so the yj, they are like this, right? So then they are, so if you, they are, is that what you say?
Right, something like that. So at time t equal to 0 or something, like, do they concentrate at a point or something, or?
No, I mean, it's like, it's a distribution like, like this. Right? So it's t minus this. So that would be like 0 in that case. Because,
okay.
it's a normal distribution to this, right? So,
and it never concentrates to a point anywhere.
No.
Okay, all right.
It's like, because it's like, I mean, if we're taking, I'm sort of a, what I meant to say here is really in terms of singularity, right? That you have hourglass waves, they like a spherical wave that comes here, but they, see here, they are not really spherical in the sense of the wave itself. They are this in terms of singularities. That's what I meant to say. The singularities are on the cone, right? But then the thing itself is not a delta function. It's just
okay, all right. So my question related to this is that, so wherever these questions arise, these such inverse problems, does it make sense to talk of only having the so-called far field data or the scattering data for just a single incoming wave, single initial data?
yeah. I mean, you mean so you you're saying instead of taking
The full operator, just the response corresponding to one initial. Does that make sense? There's such problems.
so you want just one
Right, because the problem, I mean, it's not a linear problem, so it's not to analyze it like this, but it's in some sense an overdetermined problem.
oh yeah, this one is really you just have one function on one variable, right?
Right.
Yeah, it makes sense. Absolutely. I mean, I would say, yeah, I mean, this is really an overkill in some sense because you know a lot, right? And you're just trying to recover a function from one variable. But I mean, I don't know of any other way. I mean, maybe, you know, of course, this problem is like, maybe you can use some other way, you know, sort of a Gaussian beam solution, or maybe, but also, if you do something like that, maybe you recover some X-ray transform or something. But my fear is that this potential is sort of weird, you know. Even if you know the X-ray transform, it's a radial thing, but they also put on a cone, and sort of I don't know what would be. But absolutely, yes.
So this is related to two questions that were that I had in mind. So one was, you know, is there a theory for the forward problem in one dimension? Can you define a scattering operator in one dimension? Because then, you know, the overdeterminedness is less.
Yeah, that for semilinear equation in one dimension.
Right.
That I don't know. I think it's you know, because this exponent here is sort of a, you know, is all because of three, you know, this whole scattering theory here is based on the power of this thing is a real, is a real, you know, dance in some sense, because, you know, everything here has to match perfectly so that this all works. But I suppose there is, you know, one dimensional, yeah. But I'm not, I don't know.
Okay.
Yes.
Okay. Thank you.
Of course. Yeah.
Thank you very much. Are there any other questions or comments, please?
Yeah, this is kind of strange. I mean, because you see, in some sense, this is you know, it's a really overdetermined thing. But on the other hand, I mean, I was not aware of any other result involving a, you know, determining a C infinity function. It's you know, it's like all the previous results are so you determine some sort of Taylor series, you know, for the real analytic function. So it seems to me somewhat, I don't know.
So what I have in mind is, you know, so there are, so for the linear equation, there are methods which are for overdetermined problems, and then there are a few methods which work sometimes for some problems for formally determined problems. Right. So that's what I was trying to think of the analogy.
I see. Yeah.
So, but of course, the nonlinear, you know, the nonlinear equation, you know, what is overdetermined and what is
right.
Not so clear.
Not so clear. I agree.
Okay. Are there any other questions or comments, please? If not, thank you very much, Antonio, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much.
Well, thank you.